This is part 12 of the series Calculus Prerequisites, and in this part we're going to start out with points of intersections of functions. Now, as you remember, when we deal with two functions, let's say we have this cubic and this quadratic, where they intersect, both the x and the y of each one of these equations is equal, but only at the points of intersection. So what we can do is we can set these two equal to each other because this y and this y are going to be equal and solve for x. Those x values will be the x coordinates where the graphs of these functions intersect. Then we take those x coordinates, plug them into one of these two values, one of these two equations, and we can get the y coordinate of the intersection point. So that's what we're going to do here. Let's start out with this first one, and we're going to set these two equations equal to each other. So we have x to the third minus 2x squared plus x minus 1 equals negative x squared plus 3x minus 1. So all these terms I'm going to pull over to this side because we have a positive x cubed here. So this gives us x to the third. We're going to add x squared, so that's minus x squared. We're going to subtract 3x, so that's minus 2x. And then we're going to add 1. And so when we take 1 away from 1, that gives us a 0. So we'll just set that equal to 0. Now we have this cubic function, and this came out nice and even because we have a common x here. So we factor out that x, and we have x squared minus x minus 2 equals 0. Now we simply factor this quadratic. We have x and x. We have a minus sign, so this is plus and minus. And since this is a 2 and this is negative, we'll put the 2 on the negative part. So x squared minus 2x plus x, that gives us our negative x minus 2. So these are our three factors. So now using the zero product rule, we know that one of the x values has to be a 0, because this has no equivalent expression, so x equals 0, then x equals negative 1, and x equals 2. Then we can put these values inside here, and when we put a 0 in for this, we get, so let's say that's 0 plus 0 minus 1. This first point is going to be 0, negative 1. Then we do the same thing for negative 1, put it in for this. So we have a negative 1 squared plus 3 times negative 1 minus 1. That gives us negative 1 minus 3 minus 1, which is negative 5. So this point then is negative 1, negative 5. And then the last point is going to be negative 2 squared plus 3 times 2 minus 1. So this gives us negative 4 plus 6 minus 1, which gives us 1. So the graphs of these functions cross in 3 places. Now let's look at the next problem. Here we have a simple radical expression, and down here you should be able to recognize this as a semicircle, the upper lobe of a semicircle, and it looks like the center of this is going to be at negative 2, 0. Now hopefully you can recognize that, but it doesn't really matter one way or another. The way we do this is the same way we do this. Set these equal to each other because at their points of intersection, these y values are going to be the same. So let's go ahead and set them equal. So we have square root of x plus 6 equals square root of negative x squared minus 4x. Now in this case, to get rid of these square roots, we're going to square both sides. So that gives us x plus 6 equals negative x squared minus 4x. Let's pull all the terms over to this side because this is a negative x squared here. So that gives us x squared. When we add 4x plus x is plus 5x plus 6, and that equals 0. So now let's see if we can factor this. So we have x and x, that's a plus sign, so both of these are the same and they're going to be that sign. And factors of 6 that give us 5, well that's got to be 2 and 3. X squared plus 3x plus 2x, that's my 5x, plus 6. So there we go. So our x is negative 2 and negative 3. Now we'll probably use this one. That's probably the easiest to get our result. So let's put in a negative 2 there. So negative 2 plus 6 is 4. Square root of 4 is 2. So this first point is going to be negative 2, 2. And the next point is going to be negative 3. Let's see what that comes out to. So for negative 3, I'm not going to be able to do that in my head. Well, yeah, I am. It's the square root of 3. That was because we had 6 minus 3, so that's the square root of 3. So there's our 2 points. All right, well that's points of intersection. Now what we're going to look at is we're going to look at symmetry of functions. Recall that there were 3 fundamental types of symmetry. There's y-axis symmetry, where the graph can be reflected across the y-axis and mapped onto itself. There is x-axis symmetry, where the graph can be reflected across the x-axis and mapped onto itself. And then there's origin symmetry, where the graph can be reflected across the y-axis and the x-axis, and that gives it origin symmetry. In y-axis symmetry and origin symmetry, these two are functions, and by definition, if a relation has x-axis symmetry, it can't be a function. The tests for the various types of symmetry are, first for y-axis symmetry, if f of x equals f of negative x, then the function has y-axis symmetry. In other words, if you replace the x value in the expression with a negative x value, then, and these two functions come out the same when you solve, then you have y-axis symmetry. For x-axis symmetry, it's if f of x equals negative f of x. In this case, you replace the y value with a negative y value. And in origin symmetry, you replace both the x and the y with a negative value. Let's take a look at a quick example for these 3 here. So you can see here, we replace this x value with a negative x value, and we solve. And you can see that negative x squared is still x squared, so these two expressions are equal. Therefore, f of x, which is this, equals f of negative x, which is this, so this is a function and it has y-axis symmetry. For x-axis symmetry, we replace the y with a negative y, so here we replace the y value with a negative y value. Negative y squared is still y squared, so these two are the same equations. Therefore, this is a relation that has x-axis symmetry. And then we replace both the x value with a negative x and the y with a negative y and solve. And we come out with the exact same expression. Therefore, this is a function and it has origin symmetry. All right, well, that's, again, just a really brief overview of symmetry. We also call y-axis symmetry an even function. So if a function has y-axis symmetry, we say it's an even function. And if it has origin symmetry, we say that it's an odd function. So now let's move on and let's talk about domain and range of functions. Domain is simply the set of all values in the independent variable for which the function is defined, which means if we have a function that's not defined at any particular x value, then that x value is outside the domain of the function. So it's the set of all x values where the function exists. The range is the set of all values of the dependent variable that result from the inputs of the domain values. So the domain is the values of the independent, and the range is the values of the dependent variables. So let's take a look at a couple of examples. Now here we have a simple radical function, and recall that radical functions are not defined for negative values. So this discriminant, the value inside the radical, has to be greater than or equal to 0. So we're looking for the values of x that make the discriminant greater than or equal to 0, and that's where the function is defined. So let's do that first. So we want x minus 1 is greater than or equal to 0. Solving this for x is greater than or equal to 1. So the function exists wherever x is greater than or equal to 1. Therefore, the domain of this function is where it exists, so we can say the domain is where x is greater than or equal to 1. This is inequality notation. We could have said it like this: 1 to infinity. This is inclusive, so including 1 to infinity, non-inclusive. This is the domain. You could have also used set notation. You could have said the set of all x such that x is greater than or equal to 1. It's up to you how you want to do that. But these are the different notations to describe the domain of our function. Now the range of our function, when we put in this value of 1, what is the range of this function? Well, it starts out at 0. And since this is an increasing function, then we know that the range is going to be, we're going to start at 0 inclusive, it could be 0, and it could go to infinity. So the domain is 1 to infinity, the range is 0 to infinity. Now in this next problem, we have a rational expression, and in rationals, the denominator can never be 0. So the trick is to find out where this function doesn't exist. The domain is everywhere else. So what I'm going to do is I'm going to set up the equations and we'll step through them. What we're looking for is where the denominator is equal to 0. So we set this down. This is a difference of 2 squares, so we break it apart. And our x is 2 and negative 2. This 2 and negative 2 are vertical asymptotes, and that gives us a domain where x doesn't equal 2 and negative 2. Now to find the range, we have to take these vertical asymptotes. Now notice that as this function approaches 2 from the left, it gets increasingly negative because this denominator is negative, so it gets increasingly negative, so it goes to negative infinity. As it approaches 2 from the right, it's positive, so this expression becomes increasingly positive and goes to positive infinity. If you remember the laws of horizontal asymptotes, since the denominator is increasing faster than the numerator, this function never reaches 0. So 0, y equals 0, is a horizontal asymptote. And the simplest way to specify that is the range is y doesn't equal 0, which means it equals everything else. All right, well, that wraps up this portion, and we'll go on with another set of topics in the next video, so I will talk to you in the next video.